So I just wanted to start with a slide from last time we didn't get to. Last time we covered convexity of sets and functions, and the last slide I didn't get to from the lecture had an example of a convex function that I think is fairly prevalent in a lot of stats and ML applications, so I wanted to just go through it. So this is an example of a function that's not obviously convex. If you were to, somebody were to stop you in the middle of the street and say, hey, is this convex? Which, who knows, maybe happens to, maybe it doesn't. But I'm not sure you'll be able to say yes or no right away. But after seeing this example and after seeing it come up so many times, I think, yeah, you'll internalize this as being a convex function. So it's called by your textbook, the Boyd and Vandenberg textbook, as the log sum exp function, because it's the logarithm of a sum of exponentials. Very descriptive. The function is function, let's say, from Rn to R, g of x, and it's equal to the log of the sum. Or I guess here I have as a function, yeah, right, from Rn to R, but of sum of k terms. And each term is e to the affine function of x. So e to the ai transpose x plus bi, where ai is a vector in Rn and say bi is a scalar. This is a convex function of x. So like I said, log sum x function is what the book, your supplementary textbook calls it. Often it's called the softmax in say machine learning or even in other kind of applications. It's because this function approximates the max. So actually this function itself right here, log sum of exponentials of e to the xi. So that's a special case of this function where each of the bi's are 0 and each of the ai's is just the standard basis vector for the ith dimension. So it picks out just one component of xi. This function here, this approximates the maximum of x1 through xn. So you can kind of see that intuitively in that if, let's say, xj was a lot bigger than the rest, then e to the xj is going to be a lot bigger than the rest of e to the xi. And the sum of e to the xi over all I is going to be dominated by e to the xj. And when I take the log of it, it's basically just going to give me the log of e to the xj, which is going to be like xj. Right? So that's like the intuition for why it approximates the max. You can actually formally see that this is in between the max and the max plus log n. So it lies in between those two. All right, so how do we show this is a convex function? So first we're going to use one of our rules we know, which is that affine compositions of a convex function is still convex. So we're going to actually take this problem and to show that it's convex, we're going to actually just show this function is convex. And then we're going to cite that this function is just an affine transformation applied to this function is g is f applied to an affine transformation of x. So g is f of ax plus b, where a is the matrix that has these guys as rows, and b is the vector that has these guys as components. Okay, so hopefully that makes sense to you. And this is a lot easier to work with. I mean, mostly because the chain rule is frustrating, and I don't like to do any calculus that involves linear transformations if I can avoid it. Of course, we could have done it with this as well, but it's just nicer not to have to deal with that. And to show this is convex, we're going to actually use the second order characterization. So we're going to take two derivatives of this function, and we're going to show that Hessian matrix, which is the matrix that collects all the second derivatives across all the dimensions, is positive semi-definite for all x. Remember, that was a necessary and sufficient condition for convexity we learned from last time. It's the second order characterization for convexity. It says basically that the function is curved upwards. In one dimension, it actually literally means that, right? The function is curved upwards. So pretty much everything we need to know is actually on the slide. It just requires a little bit of calculus, right? The first derivative with respect to, say, the variable xi of this function is just e to the xi over, actually this function, right, over the whole term inside. That's just using the chain rule. Right? The derivative of log is 1 over, derivative of log t is, say, 1 over t. And then we're using the chain rule here to further differentiate with respect to the variable xi, and so we just get a single term e to the xi over the sum. That's the gradient vector in the ith component. So does that make sense to everybody? The Hessian is given by, the ith jth entry of the Hessian is given by further differentiating this with respect to xj. Okay? Right? Because just brush off the rust in case you forget what a Hessian is. The ith jth element is just the derivative with respect to xi and then xj, or vice versa. It actually, for a continuously differentiable function, those are the same thing. You can do it in either order. So I basically look at this, and I further differentiate this with respect to xj. And so now I have to use the product rule for differentiation, right? I'm going to think about differentiating the numerator with respect to xj, and then multiplying 1 over the denominator, and then doing the reciprocal, right? Multiplying the numerator by the derivative of 1 of the denominator with respect to xj. And so the numerator, basically, I get either 0 or I get this term for the derivative of the numerator if I is equal to j. So that's why this first term has an indicator that I is equal to j. Okay, and then I get, when I multiply the numerator by the derivative of 1 over the denominator, I get e to the xi times the quantity e to the xj over the denominator squared. Again, we're just using the chain rule there. And there's a negative sign because when we differentiate 1 over x, or 1 over t, say, the answer is minus 1 over t squared. That's where the negative sign comes from. Okay, so that was all like a verbal explanation of this. This really should make sense to you. If this doesn't, then make sure to look at the supplementary review notes for this kind of stuff. We're going to assume at least this level of facility with this kind of calculus from now on. So that should be hopefully clear to you guys. You can also come talk to me or the TAs if it's not. So we've derived the Hessian, and we've written it basically as a sum of two terms, two matrices really. The first is a diagonal matrix. So this is these terms actually, when we think about their action over all I and j, they just account for a diagonal matrix. I'm calling it diag z, where z is, in the ith component, has exactly this, e to the xi over the sum of all those terms. Right? Because look, I have the indicator here, I not equal to j. And this you can convince yourself, actually, if you were to think about what z is and think about the outer product, zz transpose, this is actually just exactly zz transpose. If z is e to the xi over the sum of e to the xl's. Okay, so this matrix, the Hessian matrix, looks like diag z, diagonal matrix with z on the diagonals, minus zz transpose. And it's our goal to prove actually that that is positive semi-definite. So we can do it in a bunch of ways. One way that's quite easy, which I just put on the slides because it's yet another fact to recall, or just to tell you if you haven't seen. A sufficient condition for a matrix to be positive semi-definite. What we've learned what that means, it means that, or you know what that means. It means that all the eigenvalues are non-negative. It also means equivalently that A transpose the matrix times A is bigger than or equal to 0 for all vectors A. Those are kind of the exact definitions. A sufficient condition is actually, for positive semi-definiteness, is that the matrix is diagonally dominant. So a matrix is diagonally dominant, we'll call a matrix A. It's said to be diagonally dominant if I look at its diagonal entries and I add up the absolute values of its off-diagonal entries in each row. And I have this relationship. The diagonal entry is bigger than or equal to the sum of the off-diagonal entries in absolute value. So it's called diagonally dominant. So it means that equation holds for all rows I. Okay, so it turns out that if this is true, that implies that a matrix is positive semi-definite. It's a fact from linear algebra. Okay, so sometimes it's easier to check this condition than it is to check positive semi-definiteness, although this is not a necessary condition. Okay, so you'll miss some things if all you ever go off is this definition, but at least you can try checking this first. And if it works, then it means that the matrix is positive semi-definite. So that's really the easiest way to see this is positive semi-definite. In fact, we just stare at this and we think about summing this up over all j. Right? Because this is the ith jth entry. So the ith entry is actually given by basically this, right, minus whatever the ith entry is here. If you sum this up across all j, you'll see actually you get equality here for this matrix. So that's perfectly fine. It's still diagonally dominant. You can basically see what happens is that if you sum up what happens here over j, then this is going to cancel. Right? One of these sums is going to cancel with the squared. So will you get equality? I'm not sure if that was right. Yeah, you might get equality. Anyways, it's going to be diagonally dominant. And like I said, the simplification is that this term is going to reduce to e to the xi over the sum when you sum it up. Okay, so go ahead and check that offline. And that proves that the Hessian matrix is positive semi-definite. Okay, so that was an example of, I guess, combining a few different techniques to prove convexity. Luckily, now that you know this one, you can just remember that. So log sum of exponentials is always a convex function, and you'll see it a lot. What's an example problem that uses this type of function? An example model, say in statistics or machine learning, or elsewhere. I'm sorry? Sure. Yeah, definitely. Another example that I was thinking of is logistic regression, right? So if this looks like the piece of the log likelihood for logistic regression, basically, or multinomial regression. So yeah. Okay. Any questions about that? Okay. Any questions about any of the material that we've covered in the last lecture before I start today's lecture? Okay, so these two lectures, last lecture and this lecture, are especially kind of integral to the course, and everything's going to build on top of understanding convexity. Although we'll make sure you get practice with identifying convex functions and problems as we go forward. It's just really important that you feel comfortable with the majority of the notions we covered. So if that's not the case, come talk to us, or just spend a little bit of extra time on last lecture's material and this lecture's material. Okay, so this is going to be our second lecture on kind of basic notions of, or fundamental notions of convexity, and it's going to be on optimization basics. Last time, this is what we saw. In fact, we just kind of brushed up a bit on convex functions just now. And the operations that preserve convexity, especially affine composition, at least I find, are really helpful notions that you should definitely carry forward. And so here's just a really quick test of whether or not you kind of feel comfortable with some of the stuff we've done. It may look like a really nasty function, right? But the question is that a convex function? How many people think yes? How many people think no? So people seem to think that I wouldn't put it up there if it was not convex or something. That's probably true. So yes, it is a convex function. How do we see that? Let's break it down. So first of all, if each of these were convex, then the max is going to be convex. So we saw that, right? Maximum of convex functions is convex. So reduces it to checking this is convex and this is convex. So I really have no preference for which one to do. So they both seem equally bizarre. Let's just pick one, this one. Forget about the cubed and forget about the linear transformation. The L1 norm is a norm. So the L1 norm of x is a convex function. So we're good with that. How about the L1 norm of ax plus b? It's the norm composed with an affine function, so it's still convex because we know affine composition is legit. And how about the cubed? Does that mess something up? No, because it's a monotone transformation of a convex function, monotone increasing transformation of a convex function. If you go back to the composition rules, that was one of the things that worked. So these composition rules, I think you have to just have a list handy when you want to check them, because I don't always remember what they are, but that one you can at least remember. Monotone increasing transformation of a convex function is still convex. So we're good with this. How about this one? So this one again, maybe I'd break it down to the most basic level. Log t is concave in t, right, for univariate t. And if I pull out the 7 here and get rid of the reciprocal, I can make this minus 7 times the log of ax plus b. So I have minus log, first of all, which is it's now convex. If it was just minus log of 7 log t. But instead of t, I have ax plus b, which is again an affine transformation. So I have minus log of an affine transformation. Minus log is convex because log was concave, and affine transformations are OK. OK, so that was not too bad. It would have been way worse. Your life would have been maybe slightly worse if you had to prove from the definition this was convex. You would have spent a long time doing that, I think. So operations that preserve convexity are definitely important and helpful. OK, today we're going to learn optimization terminology, properties of optimization problems in first-order optimality conditions, and then some equivalent transformations. So things you can do to optimization problems that don't change their solution, basically. So I think that this stuff, you have to have seen or used or something, but I often will start saying things halfway through the course, and I'm not sure that people have I've ever told them what the criterion or objective function is. So this is just a list to make sure we're all on the same page from now on. That's an optimization problem. Remember, that's our form of an optimization problem. And a convex one is one that has the property that function f that you're trying to minimize is convex. And these inequality constraint functions, gi, are also convex. And then the equality constraints had to be affine. So I took the liberty of just writing those as ax equal to b for a matrix A and a vector b. There's no loss of generality there, right? That is representing a set of affine inequalities, hj of x equal to 0. Perfectly fine. So we can always write the equality constraints that way for a convex problem. No loss of generality. And by the way, this domain, very soon, like maybe even in these next few slides, I'm going to stop dropping the domain from this notation. And it's just going to be implicit. So if you have a log somewhere, then the variable is restricted to be positive in some notion, right? So I'm just going to stop writing the domain, and we're going to stop really explicitly talking about the domains, but they're just going to be there implicitly. And remember that they're a part of the optimization problem, and they're also part of the requirement for a convex function is that its domain is a convex set. So we're just not going to be explicit about that. So what's that function f up there? It's the function we're trying to minimize. It's called the criterion or the objective function. You can use either term. Gi is called an inequality constraint function. If x is in the domain and it satisfies all of the inequality constraints and it satisfies the equality constraints, so if it's in the domain and satisfies all of the constraints of the problem, then we can say it's feasible. So it's called a feasible point. It's feasible for this particular optimization problem. And the minimum of f over all the feasible points is called the optimal value of the convex program. So that doesn't mean I'm not talking about the point that achieves the minimum. I'm talking about actually the function value at the minimum. It's called the optimal value of the problem, or sometimes we even call this a convex program. And we usually write it as f star. So if I don't explicitly tell you what f star is, but this is the problem you're looking at, then that f star refers to this function at optimality, so the smallest I can get over the feasible set. Okay? If x is feasible and f of x achieves the minimum, the optimal value, then it's called a solution or an optimal point for the program. Okay? We also might call it a minimizer. So some basic things. Does every optimization problem need to have a solution? Let's say a solution that is in Euclidean space. It's kind of maybe a bit of a definition. I'm sorry?
Well, I'm kind of cheating because you get the answer written afterwards.
I do. It's true. I thought that might be small enough that you can't see it. Right. I should do that then when I talk about. So Go ahead and cheat. What's the answer? No? Okay. But why not? Give me an example of a program.
Do you need to have the domain is closed and bounded?
Not necessarily. So even if the domain is unbounded, we could still have a minimum, right?
Yeah.
So, but you're going the right track. Let's suppose I'd ask you to minimize a linear function, right, over all of Rn. It's not going to have a minimum, right? It's not going to achieve its minimum. It's going to have a minimum. That minimum is going to be minus infinity. So f star is going to be minus infinity. But we can't talk about a proper point in Rn that achieves that minimum. So we actually say, it's maybe somewhat of a definitional thing, but we say that that type of problem does not achieve its solution, doesn't achieve its optimal value. Okay. When we talk about SDPs, they're actually going to be an example of a non-trivial example of convex problems that don't always achieve their optimal values. So that might seem like a trivial application, minimizing a linear function over Rn. Okay, why would you do that? It's not really very interesting. But SDPs are actually interesting problems that don't always achieve their optimal values. They don't necessarily have solutions. Okay, so anyways, the solution set could be empty, is what we just said, right? If x is feasible and it's within epsilon, it achieves a value within epsilon of the optimal value, we call it epsilon suboptimal. It's just terminology. So that means f of x is less than or equal to f of star plus epsilon, but it has to also be a feasible point. If x is feasible and this particular inequality constraint, which is gi of x is less than or equal to 0, if at that point it's actually equal to 0, we say that constraint is active or tight. The constraint is loose if we have gi of x is strictly less than 0. So we'll often talk about constraints that are active or tight at the solution, right? And constraints that are loose at the solution. That'll usually be what we talk about. But this terminology applies just to any points that are feasible as well. And lastly, this one is important because I will never be clear about this distinction from now on, or very seldomly. I will call convex optimization problems, I'll use that term to refer to both convex minimization problems and concave maximization problems. It's because they're equivalent, right? If I asked you to solve this problem, minimize a function f of x subject to all of these constraints, it's actually equivalent to maximizing the negative of the function, right? You convince yourself that's true just from kind of first principles. And if f is convex, then minus f is concave and vice versa. So often if we have a maximization of a convex function subject to some constraints, and those constraints are written in a way that respect the rules for convex problems, I'll still call that a convex optimization problem, even though the criterion is actually concave. Okay, so convex optimization means either convex minimization or concave maximization, just to be clear, yeah.
Is epsilon suboptimal also used in a multiplicative context?
You mean with more than one criterion?
No, so like for example, if fx is less than equal to epsilon times x.
Good question. No, usually when I say suboptimal, I mean additive. Yeah. It's because most of our guarantees, in fact, all of our guarantees for convergence will be an additive guarantee.
Can you give an example of a problem like this? I'm just trying to understand what kind of constraints, give an example of a constraint.
Well, we'll see lots in the lecture, so you'll get to satisfy your curiosity.
Why you're saying ax to b is separate from g x greater than 0 squared? Because you can say ax is greater than b and ax is smaller than b.
Right. I'm not saying that this is representing anything that this can't. I'm just writing it that way because it's usually clearer. So when I write ax equal to b and then gi of x less than or equal to 0, I'm usually thinking about functions gi that aren't affine. And if they were, I would just wrap them into this equality constraint. It's not always the case, but you're right. I could strictly get rid of those equality constraints, and it would not be losing anything. But I guess it's just my tendency not to write them out both. Okay. So the solution set of a convex problem is just the set of all the minimizers. It's just defined as, like I said, all the minimizers of that particular problem. It can be empty. We said last time that sometimes functions, optimization problems do not achieve their minima. so it can be an empty set. And I'll often write argmin of the convex problem to be the operation that gives you the solution set. So there's a bit of an overload here of notation. If the convex problem has just one minimizer, then I usually think of this argument as returning that minimizer, not the set containing that one point. Okay, so if there's a unique minimizer of the problem, then argmin gives you it. If there's more than one, then argmin gives you the set of all of them. That's all I typically mean by that notation. I think it's usually easiest to use that. Here's a key property. The solution set of a convex problem is a convex set. Okay? Maybe something that shouldn't be too surprising if you draw yourself some pictures. The proof just uses the definitions of convexity. So let's suppose there are two solutions, x and y. We want to prove that basically the line joining them is also a solution. So let's just go through basically all the things we need to check in order to check it's a solution. First, we need to check that the point is feasible. It actually satisfies all the constraints. Well, that's going to actually come from, we did something very similar actually at the end of last lecture when we proved that convex problems don't have local minima, proper local minima. These arguments are the same as the ones we went through last lecture, so I'm not going to go through them again. They're literally the same. So you have any 2 points that are feasible for the problem, the line segment join them is also going to be feasible. Okay? Check that that the point that's on the line segment that's in the domain and also satisfies all the constraints. We went through that last time. So go back over that if you're not clear on what those steps are. And now we also just take a look at the objective function, or the criterion. If we evaluate f at, say theta x plus 1 minus theta y for some theta between 0 and 1, then by convexity of the criterion function, that's less than or equal to theta times f of x plus 1 minus theta times f of y. But each of these guys, by definition of them being solutions, are exactly equal to f star, the optimal value, right? They both achieve the optimal value. So this whole thing is just f star. So we just proved that this convex combination of x and y is also a solution. Okay? This property tells you actually an extremely, I find actually a pretty surprising but fundamental property of convex problems. And maybe I'm giving away the answers to one of the quiz questions, so I'm sorry, Shashank, if I'm doing that. It tells you the following. Or let me see if you can guess it. A convex problem can have 0 solutions, right? We learned that. It can have 1 solution if the solution is unique. Can it have 2 solutions? Just 2? It can't, right? Can it have 103 solutions? No. Can it ever have a finite number of solutions? It can't. It actually always has an infinite number of solutions, either infinite, 1, or 0. And the infinite is actually a very strong form of infinite. It's actually uncountably infinite, because everything that is on like a line joining 2 points. It's not even a countable number of solutions can a convex problem have. Right? So just make sure we're clear by that. The moment it has 2 solutions, everything in between those 2 on the line is a solution, and there's uncountably, infinitely many things on that line. So it tells you something about convex problems. Another key property of convex problems is that if the criterion function is strictly convex, remember we learned that means that it satisfies the defining inequality for convexity strictly, then that implies that the solution is unique to the problem. And another way of saying that is that this set x opt only has 1 element, so I'll often just think about writing argmin to give me that solution. Okay, so that's something that you should go home and prove. It's going to be similar to this, but you're going to see that the criterion function is going to satisfy a strict inequality with the definition of convexity, and so you can see that basically only 1 solution should exist. Okay, here's an example of a convex problem with some constraints. And the problem is called the lasso problem. It's also known as just L1 constrained linear regression. So the setting we're in is, let's suppose we have like a response or a target y. It's an n-dimensional vector. And we have a matrix x, which is an n by p dimensional matrix. Each column of x we're going to think of as containing a feature or a predictor that we're going to try to use to predict y in a linear fashion. So we're going to take a linear combination of the columns to form a prediction of y. So if we just did regression, then that would be minimizing the least squares loss between y and x beta. So this is the L2 norm squared of y minus x beta. I'm just writing out regression, the regression loss, which you would have seen in a lot of other classes, but just in a matrix form because it's more concise that way, convenient. The lasso problem actually imposes a constraint on top of that. It constrains the L1 norm of these coefficients beta we're trying to estimate to be smaller than or equal to s, where s is just some constant that you pick. Okay, so I'm probably not going to spend very long motivating the lasso. I'm not going to spend very long motivating most of the problems we study in this class. The hope is that you've seen these problems before, that if you haven't seen them, you've seen something similar to them, so that you can go offline and motivate them by looking at previous course notes. I'll just say a few words about each. So the lasso problem, which we'll revisit because it's a nice problem from the perspective of optimization, it's nice because it imposes sparsity in the solution. So if s is small enough, then we're going to have the property that many components of s are going to be 0 at optimality. And for the purposes of machine learning or statistics, that's important because it tells us that some features the lasso problem believes are irrelevant for prediction. Right? If there's a 0 coefficient in spot 5, then the fifth column is not contributing at all in the linear model of y on x. So it performs what we call feature selection or variable selection. That was my kind of explanation of why you would use the lasso. We'll see lots of things about why it gives sparsity, why it's tractable optimization-wise, all that stuff. We'll study that in the class. We just won't motivate the problem itself for its like statistical or machine learning capabilities that much. So let's just go through all the terminology we learned. I know that this is very, very easy, but we'll go through it anyways. Is this a convex problem? Yes, I already said it was, but you can see that the loss is an affine transformation of the L2 norm squared, which is convex. You can also see that if I take the second derivative of the loss twice with respect to beta, I get out x transpose x basically as the Hessian matrix, which is always positive semi-definite. Right? We said that already. If I take the cross product of any matrix with itself, like x transpose x, for example, that's always positive semi-definite. And the constraint, there's just one constraint, and that's a norm constraint on beta, and norms are convex. Right? So it's a convex constraint. And s is a constant. So I could write this as, norm of beta 1 minus s is less than or equal to 0. That would be the inequality constraint function. So I just have one inequality constraint. And the criterion, as you guys all know, I'm sure, is just this guy, right? The optimization variable here, by the way, is beta. Okay, so that's the setup, and we have no equality constraints. The feasible set is just the set of all points that lie within the L1 ball of radius s, right? That's the feasible set for this problem. The domain is everything for both of these functions, and there's only one constraint. So that's the feasible set. It's this guy. Now let's break it down. Is the solution unique? It's a question that, see if we can answer. Is the solution unique? In two cases. What happens if x is full column rank, which means that n must be bigger than or equal to p? So what happens if the columns of x are linearly independent? Sorry? The solution is?
There are either 0 or 1 solutions to.
So how could there be 0 solutions to this?
If you've got linearly independent rows, and then the y is not a specific span of those rows.
Okay, but that would mean that I don't get equality between y and x beta, but I would still there would still be a beta that is closest to y in the L2 norm sense, right? So I know, but I hope that you guys can see this. There is always going to be a solution. The solution set is bounded. So first of all, you can't go off to infinity anywhere. And there's actually, in the case that x is full column rank, there's just going to be one solution. And a way to see that is that if I take, let's just go back to what I said the Hessian was. The Hessian of the loss function, so which I write as this, as a function of beta, it's just going to be equal to 2 actually times x transpose x. And if x has full column rank, then this matrix is invertible. Because this is a p by p matrix. I told you that each of the p columns were independent. This is going to be strictly invertible, which means this is actually strictly positive definite. So it's more than positive semi-definite, strictly positive definite. And if you go back to the slides from last time, that was sufficient to imply strict convexity of the criterion function, more than just convexity. And as we said last time, strict convexity of the criterion implies uniqueness of the solution. Okay, so we're good on that, hopefully. How about if p is bigger than n? So I'm trying to make a prediction, but I have more features than I have observations. So I'm in what we call high dimensional case for this kind of problem. It's not necessarily unique, right? Because this is going to be singular if p is bigger than n. So the criterion is not going to be strictly convex. One very surprising fact, which we may go through when we talk about the KKT conditions, that actually this problem is fairly special. And even when p is bigger than n, the solution is almost always unique. It's unique with probability 1. And I'll just not explain what that probability is being taken over. But if we go through this, when we talk about the KKT conditions, then I'll be more precise. So just goes to show you, strict convexity is not necessary and sufficient. It's sufficient, but there can be problems that are not strictly convex, like this one when p is bigger than n. So we can't say from general convexity theory that they should have a unique solution. But if we study them more carefully, then they may still have a unique solution, even quite broadly, like this problem. OK, think about how our answers would change if we changed the loss function to this guy. So this is called the Huber loss. I'll leave that for you to think about offline. It's still a convex loss, but just think about how all the answers would change, particularly the answers about uniqueness. Might be interesting to think about. The other problem that we'll see quite a bit in this class is SVMs. So lasso and SVMs, they're both very nice from the perspective of optimization because we can solve them, of course, quickly. So we'll go through algorithms for each of them kind of quite extensively. And again, I hope people have seen this, or at least have seen something very close to this. But the setup is now a classification setup rather than a regression setup. And let's say y takes labels either -1 or 1. And I have n of them. So this notation just means that y is an n-dimensional vector, but every element is a -1 or a 1. And again, I have features x, p features, each one along the columns of this matrix x. And I'm going to call the rows x1 through xn. So lowercase means the rows. And the SVM problem, support vector machines problem, is the following. I have actually 3 parameters in the optimization problem. Beta, beta naught, and I always forget what this is called. Every year this is a psi, I think. Is psi, okay. I confuse it with zeta, I think, a lot. Psi. So the loss here is the 1/2 the L2 norm of beta squared plus some c. This c is again a constant, just like the S in the lasso problem. It's a constant, which is actually tuned by the user of the SVM problem, times the sum of the psi i's. And the constraints are that each of these psi i's should be non-negative, and that each label yi, if I multiply it by xi transpose beta plus beta naught, that should be bigger than or equal to 1 minus psi I for all I going from 1 through n. So again, I'm going to spend very little time motivating these types of problems, but I'll just draw you a picture so that you kind of can interpret what a lot of these quantities mean. Xi transpose beta plus beta naught, if I think of xi as the variable, that's defines a hyperplane in Rn. Okay, and asking that basically things lie on one side or the other is as asking that things lie in one half space or another. So what this problem is trying to do is trying to find a linear separator of the two classes, one that have labels -1 and one that have labels 1. But you can see we're not asking for strict separation, because we're not asking this is actually bigger than or equal to, say, 0. We're allowing for a little bit of slack. That's what these variables are called. Psi I are called the slack variables. So basically, one side of this hyperplane maybe is going to be the +1 side. and one side is going to be the minus one side. And in solving the SVM problem, we're going to hope to find a hyperplane that has most of the minus one points on the minus one side and most of the plus one points on the plus one side. Okay, or these could be switched, right, in terms of the roles of these two classes. And this actually, if you look at the derivation of the SVM problem, this determines the margin of separation. This, the L to norm of beta squared actually is a normal vector to this hyperplane. So this actually, you can kind of intuit, controls the margin of separation. Okay, so if beta naught is small, if the L to norm of beta is small, that means that we have actually very good separation. So it's reciprocally related to the margin that separates the two classes. Psi I are the slack variables. I already explained what those are. So we pay some price basically for them. You can see in the criterion. So I could have, for example, a minus 1 point here. This could be a point yi that could be equal to minus 1. And so I could be getting it wrong, and I pay some price for that. That would be psi I here. This, I said, by the way, this margin is actually like 1 over the L2 norm of beta squared. That's what this margin is. And beta naught is just the intercept. So this controls where this is lying in space, some offset, and it's not penalized at all, right? We can put this wherever we want. So that's the...
Start from the minus 1.
What, sorry?
I think the psi I should begin at the minus 1, the line.
The margin?
Yes, from here.
Yeah, you could be right. I think that's true, yeah. Right, thank you. Okay, so that's the SVM problem. Let's ask the same questions that we did before. Is this convex? So yes, it's convex. I won't poll you about that. I assume that you guys have seen this before and have dealt with it before. It's actually has kind of 3 variables you have to think about, but they all contribute in a convex way to the criterion. We have a quadratic form in beta, it's just the L term of beta squared, and we have a linear term in psi I. It's just actually, think about it, it's the vector of all 1's transpose psi I. That's what that is up there, and beta naught doesn't appear at all in the criterions. The criterion is a convex function of that triplet. And all the constraints are convex ones, right? I have just an inequality constraint on psi I, and this is just one big affine inequality. If you unravel the involvement of beta naught, and psi I, it's just one big affine inequality here. You move it all to one side if that makes you feel more, if it makes it more transparent. So yes, it is a convex problem. The criterion is this guy. The constraints are all of these. So now we actually have, in a sense, less succinct constraints than we did for the lasso. The feasible set is the set of all points that have positive slack or non-negative slack and that satisfy this inequality with the half space inequality. And let's ask this question: is the solution unique? How many people think the solution is unique? How many people think it's not unique? So we had, again, pretty underwhelming participation. I have to figure out a way to get you guys to participate more. Maybe I'll bring candy or something and throw it. Whoever thought it was unique, why do you think it's unique? I know that's not always fun to voice the answer out loud, but a brave soul, why do you think it's a unique solution here? Okay, who thought it was not unique? And give me an explanation for that. Yeah.
You have 1 point, say y I equals -1 as in the figure there, and you could have separators like the dashed lines that we've drawn. You could have more than one of that, which satisfies the same exact problem.
Right. So it's a good intuition. You're thinking about the problem in particular, which is one way to answer it. It was not the way I was like kind of hinting at, but yeah, you're right. You can think about a configuration of points where I could get the same margin, but maybe by rotating that separator somehow. So I get the same margin, I get the same kind of slacks, so it would not be unique. How about if we look at the problem itself? So Remember, the variable here is the big variable is called like z, beta, beta naught, psi. It's a triplet of those three. Is this strictly convex in z? It's not, right? Because it has this linear component in one of the parts of z, psi I. So if I think about the role of the slacks, then if I try to, for example, take one feasible point, another feasible point, and I evaluate the criterion on a line segment joining them, this part's actually going to be equal, right? Or I'm going to get an equality for that part of the for that convex part of the criterion. I'm not going to even get an inequality there because this is linear. So we don't have a strictly convex criterion, and it's not necessarily unique according to our kind of convexity theory. What happens if I change the problem and I just put a psi I squared there? Is that strictly convex? Still missing something. I'm missing beta naught. It doesn't appear anywhere in the criterion actually, right? So it's not strictly convex with respect to beta naught. And again, it's going to be equal for any two different points of beta naught. So what if I put psi I squared plus beta naught squared? Then it's going to be strictly convex, right? Because everything kind of appears in some squared form in the criterion. But that's not a very interesting problem. You don't want to penalize the intercept, right? That doesn't seem like it. That would be penalizing the intercept variable. So I'll be telling you, you want to make this hyperplane very close to 0 in terms of its offset, which is not really a very good idea. OK, so that was this down here. Very important property of convex problems, we learned it last time, just to repeat, is that local minima are global minima. The proof follows from the definitions. Here were two pictures. I drew a convex surface and a non-convex surface. This was just two different criterion functions you might have in R2. And just showing you that, actually we'll see this picture again when we talk about gradient descent. But you can see that basically there is only one minimum here, and it's globally optimal. Even if actually this whole line was flat, it would still be the global optimizer. If this was like a kind of like a piece of paper that you just bended, it could still have a non-unique minimum but still be globally optimal. And for non-convex problems, that's not true. They can be much more exotic in terms of exhibiting local minima that are strictly better than anything else in their neighborhood but aren't globally optimal. So something people often confuse, I find this even later in the course, is that they think that somehow because a problem's convex, it has to have a unique solution. I think that just kind of gets somehow confused later on. That's not true, right? We already said that a convex problem could actually have infinitely many solutions. The difference is that a convex problem has a convex solution set. So don't confuse no local optima with not more than one optima. It just means that any optimum that you find is globally optimal. Okay? Why don't we take a break? Let's take a quick few-minute break, and then we'll come